So I'll start here. Good morning, everybody. I'll talk about some of the activities that is going on or that are going on at the moment within the preparation for this the CIMR, which is the sort of Copernicus imaging microwave radiometer. And I think Stefan touched upon and mentioned this satellite yesterday. And I'll mention a little bit more in detail on some of the aspects of CIMR and give a sort of brief overview of some of the activities, and then go in more detail on the activities that we do at DMI in terms of the sea surface temperature retrieval and the preparation for the algorithms. And it's mostly work, I should say, done by Emi Alaskans, who's working at DMI. So the Copernicus imaging microwave radiometer, we heard yesterday, it's a mission, a new satellite mission, which is sort of sponsored or paid by for the European Union and developed in collaboration with ESA and also EUMETSAT. And it's 1 out of 6 new Copernicus EU Copernicus missions. We call them expansion missions, covering different aspects of Earth observations. And CIMR is one of the polar missions. So its main priorities is to monitor the polar regions and to increase the observational density of satellite observations in the polar regions. And the key variables for the mission are to retrieve sea surface temperature and sea ice concentration. Those are the two primary variables to retrieve accurately and with high resolution. But in addition to these two variables, we also have a lot of other variables like sea ice thickness, sea surface salinity, ocean vector wind speeds, soil moisture, and in total, I think it's more than 25 different products that will be coming out of the mission. It has a swath width of 1900 kilometers, meaning that it will observe 95% of the globe every day, and there will be no hole at the pole. Everything will be covered. And also it has very strict requirements, is in particular for the sea surface temperature and unprecedented requirements for microwave SST retrievals, that it should obtain the SSTs globally better than 0.2 degrees Celsius and with a spatial resolution of 15 kilometers. As I said, it's a collaboration between EU, ESA, and also EUMETSAT. So the work has been divided in terms of the algorithm production and the product processing, so that ESA they are responsible for the polar products, whereas EUMETSAT will be responsible for producing and developing the global ocean atmosphere products. So within this, and maybe I forgot to mention, but it will also come in the end, but the expected launch of CIMR is 28-29. So we have some time to prepare and to develop these activities, but there is also quite a few things to do. I'll come back to that. And the activities have started already. The CIMR is now in past phase A0B1. So it's actually being built. And the design is more or less over, and then we're starting to. The industry team has started to construct the actual satellites and see how that can meet the requirements. So there has been a few studies in the first phase called CIMR MRC and CIMR apps. But what is ongoing now are several studies, which is one called CIMR SEPS. All these are within ESA projects. So it's one called CIMR SEPS, which is about developing an end-to-end simulator, going all the way from the surface conditions, and then try to simulate how will that look like in the CIMR observational frame geometry in terms of top of atmosphere brightness temperature, but also how CIMR observe this. So that's the CIMR SEPS. Then we have something called a project called CIMR DeValgo, which is the first study about we're making a first HTBD version 1 and 2 of the retrievals for some of the priority products, including the sea surface temperature. Then we also have a project called CIMR Macret, which is a project that goes all the way from level 0 and try to establish an uncertainty budget for the brightness temperature for the level 1B data set, but also for level 2, and again for priority products like SST. And finally, we have a project called CIMR regridding, which is about developing a regridding toolbox due to the CIMR observational geometry is quite complex, and I'll come back to that. So the green ones here are ongoing at the moment, and then we have the yellow ones that are about to start, which are the two first ones are again ESA-funded projects. The CIMR PAD is the big project where all the development and algorithm and retrieval development and determination and tuning and implementation into the ground processor will happen. It's a 4-year project that will have a focus on 24 different products to be developed and delivered and put into the ground processor. And then we have the CIMR Air, which is about building an instrument. That's I think also just had kickoff or will have kickoff very soon. Building a microwave radiometer instrument that can be flown on airborne campaigns. And then lastly, we have EUMETSAT just had a call out for the development of a prototype algorithm for global atmosphere and ocean products that has just closed, and that will probably start in the beginning of next year. So in the following slides, I'll just focus on the work that we have done. I should say that so far in the ESA project, DMI is the responsible institution that are responsible for developing all the SST retrievals in the CIMR DeValco and in CIMR PAD, which will have kickoff soon. So that's what I will focus on here. Let's see. Yeah, so CIMR DeValco, that's a project led by the Norwegian Meteorological Institute, and it's really about developing ATPD version 1 and 2, the very first versions for the high latitude polar ocean and adjacent seas, as it is defined in the mission requirement document. We are right now we are looking into or we are working on implementing a 2-step regression retrieval. It's similar to the retrieval we used as I said, in Alaska and Sedal 2020, and which was also used to produce the ESA CCI version 3 AMSA data set, the climate data record that Owen talked about yesterday. Of course, there will be an adaptation to the CIMR frequency, and that will take place and happen in the way that we did it in this paper by Pia by 2021. And essentially, it's important to stress that all code and all documentation on the development, and that applies for all the variables, that is open and free, and that's documented in Git, and it will be in what we call Jupyter Books. It's not Jupyter Notebooks, it's Jupyter Books, which is a little bit different, but it's the first time that we are using this to combine both the code and the validation and the description and produce ATPDs in these Jupyter Books, and they are all available open and freely online, including the algorithms. So in the development, it's important to of the algorithms and retrievals. It's important to take into account the CIMR sampling characteristics, and that is quite complex, I can tell you. First of all, we have, as you know, or as was said yesterday, we have the different frequencies. So we have the L band that has a resolution of 60 kilometers or a little less, probably. Then we have CNX band, which has a resolution of 15 kilometers, and then we have KU, KA band, which they have a resolution of 5 kilometers. So we have all these different channels, 5 different channels, and they all have four Stokes, full Stokes parameters for all the channels. But then we have to combine this information into one retrieval at a given target grid point. And I should also say, in order to accommodate the low noise and the high spatial resolution on the observations, the This CIMR instrument will actually consist of 13 different feed horns. So meaning that at every scan we have there's 1 horn for L band, but we have 4 for a CNX band, and we have 8 for KU and KA band in order to allow enough time to integrate the observations and to reduce the noise, and at the same time have a realistic rotation rate. So as you can see on the lower left figure here, no, on the right figure, if we start with that, that's just an illustration of how the samples will look across the scan. So when it's scanning, we have all the different footprints located and not centered at the same position, around the same position. And also in the forward-looking scan, they are adjacent to each other, the footprints, whereas when you go to the edges, there is a lot of overlap because the previous scan also covered the edges. So there is a lot of overlap and different horns and different samples to take into account. And at the same time, the CIMR instrument is set out so that for a nominal footprint of 15 kilometers in C-band, for instance, we are going to average 5 individual samples along the swath. So it's a complex beast, and that requires quite a lot of tuning and technical details.
Jakob, can you go quickly because time is over?
Yeah, sorry. Yeah, I'll speed up. So in order to test that and work on the retrievals, we then have some level 1B simulated files where we have different surface characteristics that have been propagated through the simulator, and in order to simulate the actual CIMR observational characteristics. And we use that, I can say, just to tune our algorithm and test our algorithm performance. How do we perform close to the sea ice and close to the coast? And this is just a few results here, indicating that we actually, as you can see on the 2 figure, the closer we get to the coast, the more contamination we get. That's well known for microwave observations. But you can also see that within 20 kilometers or 20 kilometers away from the coast, we actually tend to get a very good and very low contamination of the retrievals. And we also use the screen comes down maybe in a, yeah, we also use the multi-sensor matchup database from AMSA in order to determine the coefficients and of course select it for the CIMR frequencies, and that looks again fairly okay. This is the first version, first step, and we'll then propagate all the uncertainties developed in this MACRET project. We'll propagate that through our retrieval in order to determine the level 2 uncertainty estimates as well. Conclusion. So the CIMR instrument and development is ongoing, and we have some ESA and EUMETSAT projects starting up, focused on the algorithm development activities. And right now it's a lot about resampling, how to combine the samples in a good way, in a smart way. It's about uncertainty analysis, and then of course tuning the retrievals. And later on it will be implemented in the ground processor, but that's in the time to come. And yeah, as I said, the expected launch is 28, so we have some time to do development, and that's nice because it's needed. It's a complex instrument. But everything is open and freely available, including the simulated data set. So come and see me if you're interested in working with this. Thank you.